Quick recap. So far, we have studied the system through its time response: step input, step output, settling time, overshoot. Today, we change the lens. Instead of a step, we send in a pure sine wave and ask what comes out. The answer is the frequency response, and it is the most powerful tool in classical control. Why care about sine waves? 3 reasons. First, every real signal can be written as a sum of sinusoids. That is the Fourier idea. If we know how the system handles each individual sine, we know how it handles every signal. Second, frequency response is what we measure in the lab. Drive a sweep into the system, plot magnitude and phase versus frequency. The curve we get is the system in a different language. Third, every classical design tool from here on, Bode plots, Nyquist stability, gain and phase margins, lead lag compensators, PID tuning, lives in frequency space. Master the frequency response and the rest is geometry. The thought experiment. Imagine an LTI system, a black box. Input, a pure sine wave, sine omega t. Wait for transients to die out, that is the steady state. What does the output look like? It turns out the output is also a pure sine wave at the same frequency omega. The system cannot create new frequencies, that is the linearity promise. But two things are different. The amplitude is scaled by a factor, and the phase is shifted by an angle. Both depend on omega. Send in a slow sine, you get one amplitude and one phase. Send in a fast sine, you get a different amplitude, a different phase. The system speaks a different dialect at every frequency. The main result in one line. For input sine omega t into an LTI system g of s, the steady-state output is the magnitude of g of j omega times sine of omega t plus the angle of g of j omega. That is the entire story. Two numbers, magnitude and phase, at each frequency. Where does the formula come from? A two-step argument. Take the Laplace transform of sine omega t, multiply by g of s, do partial fractions. The transient pieces decay because the system is stable. What survives are the two terms with poles at plus and minus j omega, and those combine into a sinusoid with amplitude the magnitude of g of j omega and phase the angle of g of j omega. We do not need the full derivation today. The takeaway: to find the frequency response, just substitute s equals j omega into your transfer function. The complex number you get encodes both the magnitude scaling and the phase shift. How to compute g of j omega? Substitute s equals j omega into g of s. Now you have a complex-valued function of the real variable omega. From that complex number, extract two real numbers. Magnitude, the modulus of g of j omega, written as the absolute value of g of j omega. This is the gain at frequency omega. Phase, the argument of g of j omega, written as angle g of j omega. This is the phase shift the system imposes at frequency omega. If g of j omega equals a plus jb, then magnitude equals root a squared plus b squared, and phase equals arctan b over a. Most transfer functions are rational, a polynomial over a polynomial. For those, factor the numerator and denominator, then magnitude is product of factor magnitudes divided by product of factor magnitudes, and phase is sum of factor phases minus sum of factor phases. Each factor is easy to handle by itself. Worked example. Take g of s equals 1 over s plus 1, a simple first-order low-pass filter. Substitute s equals j omega. Get g of j omega equals 1 over j omega plus 1. To find the magnitude, multiply numerator and denominator by the complex conjugate or use the rule directly. The magnitude of 1 over j omega plus 1 is 1 over the magnitude of j omega plus 1, which is 1 over root 1 plus omega squared. For the phase, the angle of 1 is 0, and the angle of j omega plus 1 is arctan omega over 1, equal to arctan omega. So angle of g of j omega is 0 minus arctan omega, which is just minus arctan omega. Plug in some numbers. At omega equals 0, dc, magnitude is 1, phase is 0. The system passes dc perfectly. At omega equals 1, the corner frequency, magnitude is 1 over root 2, which is approximately 0.707, and phase is minus 45 degrees. At omega equals 10, well above the corner, magnitude is about 0.1, and phase approaches minus 90 degrees. The system attenuates and delays high frequencies. That is the signature of a low-pass filter. One last piece: decibels. Frequency response magnitudes span many orders of magnitude. To compress the range and turn products into sums, we use a logarithmic scale. Magnitude in decibels equals 20 times log base 10 of the magnitude. A magnitude of 1 is 0 dB. A magnitude of 10 is 20 dB. A magnitude of 0.1 is minus 20 dB. A magnitude of 1 over root 2 is about minus 3 dB. And that minus 3 dB number is so famous it has its own name, the minus 3 dB cutoff frequency, the bandwidth. From now on, when we plot magnitude, we will plot it in dB on a log frequency axis. That is the Bode plot. Coming up next, the full picture. The frequency response is not just one number. It is a function of omega. For each omega from 0 to infinity, we get a magnitude and a phase. Plot both, and you have the complete fingerprint of the system. For our example, g equals 1 over s plus 1. Magnitude starts at 1 at dc, drops to 0.707 at the corner, falls off as 1 over omega for high frequencies. Phase starts at 0, passes minus 45 degrees at the corner, approaches minus 90 degrees as omega goes to infinity. These two curves are the system. They contain everything you need to predict how the system will respond to any sinusoidal input, and by Fourier, to any input. Summary: send the sinusoid into a stable LTI system. Wait for transients to die. The output is a sinusoid at the same frequency, with amplitude scaled by the magnitude of g of j omega and phase shifted by the angle of g of j omega. To compute, substitute s equals j omega into g of s. Magnitude and phase fall out of the resulting complex number. Magnitudes are usually plotted in decibels. dB equals 20 log magnitude. The frequency response, magnitude and phase versus frequency, is a complete description of an LTI system. Every classical design tool from here lives in this space. Next, we learn to draw it efficiently, the Bode plot.